Hey everyone, welcome back. In this example, we want to use our newfound knowledge to help us sketch the graph of the function f of x, which is defined in this factored form as the quantity x minus 2 squared multiplied by the quantity x plus 2 squared. So in order to sketch the graph of our function f of x here, this polynomial, we're going to need to know the end behavior and the local or short run behavior of this polynomial. It doesn't matter which one we find first, but I usually like to start with the end behavior of our polynomial. All right, so we need to remember that the end behavior of our polynomial function f of x here is determined by the leading term of our polynomial. The issue we currently have, although it's not too big of an issue, is that our polynomial f of x is currently written in this factored form, so we're going to have to do some expansion to identify that leading term. Remember, we do not need to expand this function completely, we just need to expand it enough to identify that leading term. This step I am doing right here is not necessary, but I think it may help some of us in kind of expanding this to find just that leading term. Remember, the leading term is going to be created by taking the biggest piece of each of our factors and multiplying them together. And so we have to be careful, depending on how we write the factored form of our polynomial. If we have a quantity like x minus 2 or x plus 2 squared, remember that exponent means we are repeating that multiplication. We have two factors of x minus 2 and two factors of x plus 2. So if we take the leading piece or the biggest piece out of each of our four factors for this polynomial and multiply all those together, we get x times x times x times x. We get x to the power of 4. And so our leading term for our function f of x here is x to the 4th. That means the end behavior of our polynomial is going to have the same end behavior that the function x to the 4th does. That looks a lot like a concave up parabola. Technically not, but it looks like one. And that's going to be going up as we move to the left or to the right. So now that we know the end behavior of our polynomial function, next we need to find the zeros, which tell us the local or short run behavior of our function. So having our function f of x expressed originally in this factored form is very advantageous for helping us find the zeros of our function. We know our function f of x is going to be equal to 0 if and only if these factors of x minus 2 and x plus 2 are equal to 0. So from those factors of x minus 2, we get a 0 at x equals 2. And from our factors of x plus 2, we get a 0 or zeros at x equals negative 2. And what we know about both of these zeros is that there are two factors in our polynomial corresponding to each 0. So each of our zeros is of multiplicity 2. And so that means as we approach the x-axis or the horizontal axis in the graph of this function, we have to actually bounce back and off of the x-axis as we approach these zeros. All right, so let's put the information that we know up on the board. So we know the end behavior of our function is that as we move to the left and as we move to the right, we're going to be going up. We know that we have some zeros at x equals negative 2 and that x equals positive 2. So as we move to the left and up, that's equivalent to saying as we move to the right, we have to go down from the left end behavior. So we're going to have to go down to our first 0 at x equals negative 2. And now this is where knowing the multiplicity is very helpful. Our multiplicity at x equals negative 2 is a multiplicity of 2 or an even multiplicity. So that means we have to gently bounce off this 0 turnaround at x equals negative 2 and start going back up. So because of that multiplicity of 2 at x equals negative 2, we have to turn around and bounce off our x-axis here and start going back up. But eventually, we're going to have to turn around and start coming back down again because we have to then hit our other 0 at x equals positive 2. So there is going to be some turning point where we create a local maximum between x equals negative 2 and x equals positive 2. And unfortunately, in this class, we will not be able to find the value of that maximum or the exact location. That's really something we learn how to do in Calculus 1. If I remember correctly, that local maximum actually does occur directly in the middle just due to the symmetry of the situation we are in. And we could actually find that and add a little bit of more detail to our graph if we plugged in x equals 0 and found not our horizontal intercept, but our vertical or our y-intercept. And if we did that real quickly, if we plugged in x equals 0 up here into our function, get negative 2 squared, which is 4, times positive 2 squared, which is also 4. 4 times 4 is 16. So we also know our y-intercept is at 16, just adding a little bit more of detail to our graph. All right, so we've successfully bounced off our 0 at x equals negative 2, crossed our y-intercept, and now we are heading back down to our other 0 at x equals positive 2. We also noticed that this 0 is of multiplicity 2, so we have to bounce off that 0, turn around, and start going up, and we just keep going up forever, indicated by our right end behavior for our function. Let's go ahead and jump into another example where we're asked to sketch the graph of a polynomial function that is given to us in its factored form. So again, we're calling our function f of x. This time it's defined by the equation negative 2 times the quantity x minus 1 squared multiplied by the quantity x plus 2 raised to the power of 5. All right, so the first thing we might want to find if we want to quickly produce the sketch of this polynomial function is the end behavior of our polynomial function. Remember, our end behavior is determined by the leading term. And so if we want to find the leading term, we're going to have to do some partial expansion here. So we have to put all the important factors together. We have to take the leading kind of piece of each of our individual factors and multiply those together to create our leading term. And we have to also include that leading coefficient factor of negative 2, even though it's not included in those factors that produce the zeros of our polynomial. So we're going to have a negative 2 times an x times another x. So I'll just call that times an x squared. Then from our 5 copies of x plus 2, we're going to pull a factor of x out of each of those and multiply all that together, right? So the negative 2 came from that factor that helps us create our leading coefficient and leading term. We get 2 factors of x from x minus 1 squared, and we get 5 factors of x from the quantity x plus 2 squared. Putting those together using our exponent rules, we have 7 factors of x. So we have negative 2 times those 7 factors of x. The leading term of our polynomial is negative 2 times x to the 7th. We don't need all those other terms at this point. And so now we can observe that negative 2 times x to the 7th is an odd degree polynomial that's been vertically reflected because of that negative coefficient out front. So the end behavior is going to look like a negatively reflected cubic graph. In particular, as we move to the left, we would go up, and as we move to the right, we would have to go down. So now we know enough to describe the end behavior of our function. The rest of the information we can need can now be found through the zeros of our polynomial and the multiplicity of those zeros. And this is where working in factored form is very beneficial. We can see from that first factor of x minus 1 squared, we have a 0 at x equals 1 of multiplicity 2. And from our next set of factors, x plus 2 to the power of 5, we see we have another 0 at x equals negative 2 of multiplicity 5. And now with this information we have found, we can put together a sketch of the graph of our polynomial function. So when I'm putting all this information together to graph the polynomial function, I usually start by putting the end behavior down, but let's mix it up for this example. Let's start by plotting those zeros. So we know we have a 0 at x equals positive 1. So that's right about there. Then we have another 0 at x equals negative 2. And so our 0 at x equals 1 is of multiplicity 2, so we're going to bounce off the 0. We can either bounce off the 0 from below or from above, and that's where knowing the end behavior can be helpful. And that's one of the reasons why I usually start with the end behavior, right? We know for the far right of our function, we have to go down and to the right, and that tells us that, well, from that far right end behavior, we have to eventually hit our 0 at x equals 1. So from our end behavior, we have to hit our 0 at x equals 1, but we know our 0 at x equals 1 is a 0 of multiplicity 2, so we have to bounce off that 0. So the fact that we have to bounce off this 0 along with our end behavior lets us know we are bouncing off our 0 from below. That is one way to figure out whether we bounce off our 0 from below or from above. Another way to do it is creating something that we call a sign chart that we'll see in some other examples. All right, so we bounce off our 0 at x equals 1. Our other 0 at x equals negative 2 is an odd multiplicity, so that means we're going to pass through it. But because it's odd and not 1, it's bigger than 1, it's like 3, 5, or 7 or more, that means we're going to cross through this 0, not like a straight line would, but like how our cubic function would. It's going to have that bend and sort of inflection type point at that 0. So we also know our other piece of our end behavior is as we move to the left, we have to go up. So we're going to be coming down from this end behavior, crossing through our 0 at x equals negative 2. And as we cross through that 0 at x equals negative 2, we need to flatten out and draw it as if it was a cubic function. Just don't draw it like it's a straight line because that is not accurate. Well, we know somewhere between negative 2 and positive 1, there's going to be a local minimum, a point where we have to turn around and start going back up in order to actually hit that other 0, that first one we graphed at x equals 1. We do not have enough information to know where that little local minimum is. We have to wait until we get to calculus 1 to figure that out algebraically or do it ourselves. I mean, we could find it using a calculator, but that takes away all the fun. So here we have another example of us sketching the graph of a polynomial function just by quickly analyzing the end behavior from the leading term and the local or short run behavior from the zeros and the multiplicity of those zeros.